Hi everybody. Today we will continue our discussion about lines and planes. We will start with reviewing a little bit what do we know already about equations of lines and planes. So recall that, let me write maybe first those are lines, and here are planes. Okay, so to specify a line, we need one point on it and a vector in the direction of the line. So direction vector, we can put it along the line or parallel to it. For a plane, remember that we need, as there, one point on it, but a vector that we give, which is, it's perpendicular. It's perpendicular. We call it n perpendicular vector. It's called a normal vector to the plane. Normal is perpendicular. Direction vector for a line is along the line. Okay, so we can have vector equation. It means x, y, z. It's any point on the line, can be built by putting initial point plus parameter t when t is any number. As we keep changing value for t, we will have more and more points on the line. A, B, C is a vector along the line. This is just another way of writing the same. R is a position vector for every point on that line, initial point plus t times direction vector. If we rewrite this separately for x, y, z as a three separate equation, we will call them parametric equation, and from that, solving for t, each equation will have expressions that are equal, and that's a symmetric equation. Okay, so that was those were lines. For a plane, as I said, we have a point and a perpendicular vector, and then we're writing them into point normal equation. If we remove parentheses, we need to remove them, sorry. If we remove parentheses, we'll have ax plus by plus cz, and all the constant we collect on the other side. I put d. That's called this is called a general equation. Okay, I want just to spend a few minutes to talk about vector equation of a plane. We did not discuss before, but when we can write x, y, z, any point on the plane can be generated from the one point x0, y0, x0, y0, z0, plus t, a, b, I should not write ABC because ABC is already used. Excuse me. I need to erase this. I will write simply vector V plus S vector W. Okay, so without any components. So we can think about a plane having initial point, that's the point, and two vector along, not perpendicular. Okay, normal was perpendicular, V and W, if they are parallel to the plane, okay, they are contained in the plane, then by choosing different value for T and S, you can generate every point on that plane. The same way for a line. Okay, I will talk again about the vector equation of the line. We have initial point, and then by changing any value for t times ABC, we will generate all the points on the line. Okay, we will not talk about the vector equation of the plane, so I will sort of slightly cross it. Everything here is correct, just we will not use it for now. I want you to concentrate on the equation of the vector equation of a line, parametric equations of a line, symmetric, and for a plane, point normal and general. Good. And let us start with the first example. We will check if the following lines are parallel, perpendicular, or neither. So let me draw first a quick picture. If we are talking about two parallel lines, obviously the lines do not stop, they are infinite. And vectors along the line, a direction vector of those lines. If lines are parallel, direction vectors are parallel as well. If the two lines are perpendicular, their direction vectors will be perpendicular as well. Okay. So this is how to check whether lines and planes are parallel or perpendicular or neither. Yes, we will look at their direction vector. This is our V1 for line 1 and V2. Okay. Are they parallel? Can you see that V2 is equal twice over V1? That means they are parallel. And therefore, L1 is parallel to L2. Good. Again, to determine in B now. We have again line 1 with V1, line 2, direction vector V2. Now V2 and V1 are not a constant multiple of each other. And so they are not parallel. Are they perpendicular? How to check it? I hope you know that to check if two vectors are perpendicular, means orthogonal, we check whether dot product is 0. Is it? We quickly compute the dot product V1 and V2. I hope you can see it is 0. Okay. Remember, first common component times first, plus second times second, plus third times third. So we are in the second case here. So line 1 is perpendicular to line 2. L1 and L2 just the names of lines. And the last one, if this is a V1 and V2, you can see that V2 is not a constant multiple of V1. Yeah, so they are not parallel. V2 dot V1, is it 0? Can you check quickly? No, it's not 0, so neither. Okay, so we know how to determine whether lines are parallel, perpendicular, or neither. Let us do the same with planes. Okay, and I will write very quickly, like 2 pictures. If the lines are parallel, you can see the normal vectors must be parallel as well. If the lines are perpendicular, I'll try to sketch this. Okay, I hope you can easily see that their normal vectors must be perpendicular to each other as well. Okay, so now again, it is enough to check whether the normal vectors are parallel or perpendicular or neither. So what is the normal vector for the first plane? Remember, we're to find one of the possible normal vector would be to read coefficient of x, y, and z, and that's the normal vector. Normal of a 2, we'll call this normal 1 and normal 2, 5 minus 1 minus 7. Is one multiple of the other? No. We have to check them. Maybe the dot product is 0. Can we compute this? Yes, that dot product is 0. Therefore, those those vectors are perpendicular, and therefore planes are perpendicular. You can write in words, P1 is perpendicular to P2, but I don't have a space. Okay, let's do exactly the same way. The next, can you write by yourself quickly? Normal vectors. Maybe pause the video for a moment. Make sure you write it by yourself. Okay, and it will be 2, 3, 1, 2, 3, 1. It's the same vector. Okay, those vectors have the same direction, the same length. So those vectors are parallel. Therefore, pi1 is parallel to pi2. I will just use that symbol for parallel. You can write words. Again, and 1 in C is 2, 3, 1, and 2, 1, minus 1, minus 1. And we can check, is n1 multiple of n2? No. So n1 is not k times n2. n1, write them as vectors, dot n2 is not equal to 0, and the answer is neither. Okay, so they are not parallel, not perpendicular. They will intersect. There's a different angle between them than 90 degrees. Again, the last one, n1, 2, 3, 1, and 2, minus 4, minus 6, minus 2. Check. Is it clear that n2 is a multiple of n1? I hope you can see it's minus 2 and 1, therefore they are parallel, and vectors are n1 and n2 are parallel, and therefore planes are parallel as well. Okay, so we know parallel and perpendicular planes. What about now discussing whether a line and a plane are parallel or perpendicular, or maybe neither? So let me start as before, just sketching two different cases, picture for parallel or perpendicular. So I'm sketching the plane horizontal because it's easier, but it does not need to be horizontal, of course. Okay, so to imagine the plane and the line above or below that will never intersect. That means parallel. The perpendicular, okay, would be perpendicular. Okay. So what we can say about direction vector of a line and normal vector of the plane. If plane and line are parallel, normal and direction vector are perpendicular. Now, if line and plane are perpendicular, direction vector and normal to the plane are parallel. Okay, so let us now, we have here read the direction vector of the line is 1, 1, 1. Normal to the plane is 1, 1, 1. And so it's the same vector, where that's this second case. The vector along the line and perpendicular to the plane are parallel. I will write that V1 and N1, those are just N1, V1 because they are the first case. Those are parallel, but what does it mean for the line and plane? Line and plane too are perpendicular. Okay, that's this second case. What about here? We have the line 2, V2 is 1, 1, 2. Plane pi2 has a vector, normal vector, 1, 1, minus 1. Now you can see that 1 is not it's not the same vector, it's not multiple of, they are not multiple of each other, they are not parallel. What about having dot product and 1 dot, excuse me, that's V2 and 2 and 2 V2. Can you quickly check that it is 0? Yeah. So this is this case, the first case. It's the vectors normal and direction vector, the line are perpendicular, therefore the line 2 and plane 2 are parallel. Again, the V3 is equal 1, 1, 2. That's direction vector for the line. A normal vector for the line pi3 is 1, minus 1, minus 1. And 1 is not a multiple of the other. Also, when you verify V3 dot and 3, it's not 0, and therefore the answer is neither. Okay, so let us move to the next example. Determine if the following planes intersect. What does it mean the planes intersect? Okay, so think about each plane as a collection, as a set of infinitely many points. The first plane, each plane consists of points that when you plug to that equation, okay, if you plug to this value for x, y, and z to that equation, and it gives you 2. When that equation is satisfied, it means the points belongs to the plane pi2. If the point x, y, z, if you plug this to the equation 2x minus 1, y minus z equal to 3, and that equation is satisfied, means the points, that point belongs to the first plane, pi1. So in order to find intersection, means we are looking for the points that belong to both planes. That means that they satisfied both equations simultaneously. Okay. And so to find points that belong to both planes means we have to points that solve that system of equations. And I know how you know how to solve the system of equations, because there will be infinitely many points. Let me try to sketch something. So the planes intersect. Yeah. What is the, here? Of course, I keep repeating this, but you have to imagine those planes and lines, they are infinite, yeah? So when planes intersect, the intersection will be a line, it's infinitely many points. You should expect, of course, you have 3 unknowns and just 2 equations that you will have a parameter. So I would suggest you will solve it using augmented matrix, and maybe once you will write the augmented matrix 2, 3, I want you to do it by yourself. Stop the video for a moment and write reduced row echelon form of the matrix, and you will have 1, 0, minus 6. I think 1, 0, 1, minus 11, minus 1. And if we write the solution, I hope you know that you will have to introduce parameter x, y, z. For z, we will introduce parameter, and y therefore will be minus 1 plus 11t, 1 plus 6t. And I hope you can recognize that this is a parametric, we can interpret this as a parametric equation of a line. we can write it in a vector form, x, y, z. This is a line that passes through the point 1, minus 1, 0, and is parallel to vector 6, 11, 1. Yep, so this is whichever form, both of those forms. This is equations of the intersection. So there is an intersection and it is a line. Let us move to the next problem. It's exactly the same problem. I want you to try to do it by yourself. We'll just give you, as before, some steps in it. So you need to find all x, y, and z points, x, y, z, that belong to both planes. It means that they simultaneously satisfy equation x, both equations. So just to write them down. You can start immediately from writing augmented matrix for it. Do your reduction, write in reduced row echelon form of it. And what you should have, it's 1, 0, 0, 1. And I think here 17 over 8, 11 over 8. 3 over 8 minus 7 over 8. Please try it. And once you have reduced row echelon form, you know you studied this at the beginning of the course, how to write solution. Excuse me. X equal y equal. We will introduce parameter for t because it doesn't have a leading one, and 3 over 8 minus 17 over 8t minus 7 over 8 minus 11 over 8t. T is a parameter. You can write it in a vector form, but this is parametric equation of a line of intersection. Two planes intersect. Intersection is a line that has, you can read what point it's passing through, what is the vector, direction vector of that line. Okay, so now we will find a point of intersection of the following line and plane. And so I hope it should be pretty clear. A picture of that. I don't know where to put it. Okay, maybe here. So if we have a plane and a line that will sort of intersect, the intersection would be a point if they intersect. Sometimes if they're parallel, they would not intersect. Okay, so we have to find that point, we need to find x, y, z, that belongs to the line and belongs to the plane. So x equal 2 plus t, I will write this equation, parametric equations of the line. Y must be 2 plus 2t, z is equal 3 plus 0t. But this point x, y, z must also satisfy the equation of the plane. So simultaneously it must satisfy that equation. Okay, and we have system of equation with x, y, z, t unknowns and 4 equation. Do not do augmented matrix here. Okay? This system has a special form. You have already highlight this maybe. You can see that instead of x, we will replace 2 plus t. Okay? Instead of y, if we replace 2 plus 2t, and instead of z, we will replace 3. We can have if we will do that here, it will be 3 times 2 plus t plus minus 2 plus 2t plus 5 times 3 equal to 2. It's a single equation with one unknown. We just remove the bracket, isolate t, solve it for t. And please do that quickly. How many t's you have? You have 2 minus 2, 1t is equal minus 17. Okay, once we have it, if t is minus 17, we can quick write, replace it in the first three equations. You will have x equal minus 15, y equal minus 32, z equal 3, and those are coordinates of our points of intersection. 15 minus 32, 3. You see that this point belongs to the line, and we can obtain it by replacing t with minus 17. On the other hand, you can also check easily that this equation is also satisfied. So the point belongs to the line and the plane. It is the intersection point. Okay, let's do the same. Let's do the same for we have another line and another plane. And if we start with the same, we'll write x is equal 2 plus 2t. We write parametric equations of that line. Z is equal 3 plus 0t. And simultaneously, that xyz point must satisfy the equation, equation of the plane. 5z is equal to 2. Again, we replace x with 2 plus 2t. We replace y was 2 plus 60. We replace z with 3. That must be equal to 2. So the fourth equation will be just the equation with one unknown. We can write, if you will remove the bracket, you will see that the left side, the t will cancel. Can you do that? You see that the left is not equal to the right? Remove the bracket, parentheses, and you see that you have contradiction. Do it by yourself, and therefore is no solution. The line and planes do not intersect. So I probably should have find the point of intersection, if any. Yeah. Here, of the following line and plane. So there is no t that will produce x, y, z that will satisfy the equation of the plane. And if this is the case when the plane and the line do not intersect, we could have seen it already here. If this is v, maybe write if that's a vector v, and n 3 minus 1, 5. If you will check v dot n, it is, if you multiply that 6 minus 6 plus 0, it's 0. It means the direction vector of the line and normal vector to the plane are perpendicular. Therefore, the line and plane are actually parallel. Okay? And that's what we know, that's intersection. So we couldn't solve it that way. But to show that there is no intersection point, it's enough to show that this equation has no solution. Okay, let us move to the next. We will determine if the following lines intersect. If yes, find a point of intersection. So the two lines intersect. To find a x, y, z, again, we have to write x, y, z that belongs to the first line. 2 plus 6t, z is equal 4 plus 0t. And another line 0 plus s y is equal 0 plus 2s, z is equal 0 plus s. And we have to solve those equations simultaneously. Too many unknowns, too many equations. Again, we have to the highlighter, and you see that this must be the same point of the point of intersection is the same point, is the same x, y, z that belongs to the first and the second line. So x must be equal s, y must be equal to y, z must be equal to z. We will write those equations. Instead of having 6 equations, we will have just 3. 2 plus 6 t must be equal to s, 4 must be equal to s. We have 3 equations with just 2 unknown and 1 already solved for us. So s is equal 4. I will maybe write that's equation 1, 2, 3. So from the equation 3 we have s equal to 4. We can replace it to the equation 1. And we will have 2 plus 2t is equal to 4. Therefore, t must be equal to 1. Okay, so we have s equal 4, t equal 1, and we have to check the second equation. Okay? So this is only from 1 and 3. The second equation is 2 plus 6t. This 1 is equal to 2 times 4, and you have 8 equal to 8. It is satisfied. So t equal 1, s equal 4 are the solution to this system of 3 equations. So make sure you verify the third equation. So now when we know that there is a solution, s and t, we will plug them back to for the first 3, we can replace t with 1. In this one, we replace s with 4, and we will have exactly the same answer. P will be equal 4, 8, 4. Yeah, 4, 8, 4. And that's the point. That's the point when those 2 lines intersect. And we're moving to the last example of today's class. We will again try to find point x, y, z. X equal 2 plus 2t, y is equal to plus 6t, z is equal 4. See, I wrote that line slightly different form. Instead of writing 2, 2, 4 plus t, 2, 6, 0 as a point and a vector along the line, the direction vector, I sort of added already those 2 vectors. So we have first component, second, third. That's alternative way of writing the equation of a line. The second, always, if you have one line has a parameter t, if the second line will have also parameter called t, you would have to change this to another one, because those are different lines, and we have to have a different names for those parameters. X, y, z is equal minus s. Okay, and again, but it must be the same point. This is a single point, single x, y, z. So x you will equal with x, y with y, z with z, and you will have from equation 2 plus 2t is equal to 1 plus s. 2 plus 6t is equal to plus 2s, and 4 is equal minus s. Now we have 3 equations with 2 unknowns. We already know from the equation 1, 2, 3. I don't want to write augmented matrix, but it's also alternative. You just make sure you collect t's and s and constant terms on the other side. You can solve it by augmented matrix, but since we have already value of s is equal -4 from the third, if we will now do that, if we will now plug it to the equation 1, we will have 2 plus 2t is equal to -3, so t will be equal -2.5. So we have s and t. Remember, you have to check the remaining, the second equation. If you were working by substitution, make sure that you do not ignore any equation, and you have 2 plus 6 times -2.5. 6 times -2.5 equal 2 plus 2 times -4, and you can see that the left side is not equal to the right hand side, and therefore no solutions. So s equal -4, t equal 2.5 is not a solution. If you will try to put that t to the first equation, s in the order, they will give you a different point. It's not the same point, so there's no intersection. No intersection. Okay, we call those lines skew lines. Skew lines, which are lines that are not parallel, but no intersection. Okay, not parallel line that do not intersect are called the skew lines. And the easy way to imagine them, to see the skew lines, to sort of draw them, think about like two parallel planes, and one will make like the different lines that are contained in two different parallel planes, but going in different direction. You know that they would not intersect, and you have to sketch them so, such that they are not parallel. Okay, so that was the last problem for this class. I will stop recording. Okay.